Okay, let's look at example 5.7. This is using the theorem of Papascaldinus. We have a outside diameter of a pulley is 0.8 meters. So this is a big pulley. So, this is going to look like it's from it's from a distance from the other end. It's going to look like this, right? There's going to be kind of this big hollow pulley, and we're looking at it in this direction just to make things clear. Knowing that the pulley is made of steel and that the density of steel is something, determine the mass and the weight of the rim. Okay, so I'm going to say this, I'm going to erase that. It's just going to be in the way. What I'm going to do is I'm going to turn around and I'm going to do this in components. And I'm going to say this is equal to this big component up here, right? So I'm going to break it up like this. I'm going to have this component. Oh, yeah, I didn't do so good on that. Sorry. Let's try that again. Boom. Plus this little component here, well, maybe a little more like that, plus the other one that's over here. Now, you'll notice I'm going to say that this is true, but since we're only rotating about this axis, any distance here is not going to make a difference, right? Because and so I'm going to say really it's going to be 2 of these, and then I'm going to get rid of that one. Okay, so let's go through. I can call this body 1 and this body 2. Right? So for body 1, let's look at the volume of 1 is what? Well, it's using the theorem of Papascaldinus. It's the distance that the centroid travels times the area. Okay, so the area of this thing is what? It's going to be 100 by 20. Now, how far is this centroid traveling? Well, if it's this centroid, right, relative to this distance, is going to be 400 minus 10, so it's going to be 390. So it ends up, it's going to be 2 pi times 390. Hopefully that makes sense, because think of it as it's the circumference of that circle, right? So when you do this out, you're going to end up with some really large number, and then you're going to realize that volume is going to be given in millimeters cubed, but we are given the density here in kilograms per meters cubed. So I'm going to convert this right off the bat to meters cubed. So volume 1, when you divide by 10 to the 9th to account for it, it ends up being 0.0049 meters cubed. That's a cubed. There we go. Okay, and then let's look at body 2. The volume of 2 is going to be the area. So let's look at either one of these. It's not going to matter, right? So what is that area? Well, it's going to be 20 by 30. So 20 by 30, right, times the distance that the centroid travels. So this centroid is sitting, it's going to, it's 400 to here minus, so it's going to be 2 pi times 400 minus the 20. That's to get to this point, and then from here to there, it's going to be another 15. It's going to be half this distance, so minus 15. So this volume of 2 is going to be nice and small. It's going to be 0.001376 meters cubed. So our total volume is equal to V1 plus 2V2. So when you add this up, it ends up being equal to 0.00765 meters cubed. So that's equal to volume. So that's one thing that it asks for. And then it wants to know, so that is the volume, and we are supposed to determine the mass and the weight of the rim. Oops, okay, so that's just an in-between step. Now, so what is the mass of this rim? Well, the mass is going to be, this is equal to volume times density, right? So it's going to equal to 0.00765 meters cubed times the density, which is given as 7.85 times 10 to the third kilograms per meter cubed. You'll notice the meters cubed are going to cancel, and so the mass ends up being 60 kilograms. There. And then what is the weight? Well, weight is simply mass times gravity. So when you multiply that by 9.81, you get 589 newtons. There you go. That's the use of the theorem of Papascaldinus.